All right, welcome back. Today, we're going to dive into the hidden logic that powers so much of our digital world, from your code editor to your web browser. We're moving beyond simple patterns and into the realm of nested structures. Like matching up all the parentheses in your code or HTML tags on a web page. This is the secret language computers use to understand structure.
So this right here, it might look like some weird abstract math, but trust me, it's the blueprint for perfectly balanced parentheses. The rules are actually pretty simple. A structure, let's call it S, can either contain another S inside parentheses, or it can become two S structures right next to each other, or it can just disappear. These few rules are the foundation for recognizing incredibly complex code.
It's all thanks to the stuff we're about to unpack. That little grammar is exactly how parsers in your code editor can spot a missing bracket and light it up in red instantly. So, the big question is, what kind of machine can actually follow these kinds of nested rules?
To answer that, first we got to appreciate the problem we're trying to solve. Let's take a look at why simpler machines just aren't going to cut it. We have to go beyond the limits of finite memory. So you remember the finite automaton, or FA, right? Its whole deal, its defining feature, is a complete lack of memory. All it knows is the state it's in right now. It can't remember how it got there or count how many times it's seen a symbol. And that right there is its fundamental weakness.
In this slide right here, it just lays that memory problem out perfectly. An FA can easily recognize any number of A's followed by any number of B's. That's a simple pattern, no problem. But the second you ask it to recognize an equal number of A's and B's, it fails. And why? Well, because to do that, it would need to count the A's. It would need memory.
So the solution becomes pretty clear. We need to give our machine an upgrade, a power-up. We need to give it a memory. And it doesn't even have to be complicated, just a simple stack, a last-in, first-out list. As you're about to see, this one small addition, it changes absolutely everything.
So we have our upgraded machine in mind, but what kind of blueprints can it read? Well, that's where we get to context-free grammars.
Okay, so a context-free grammar, or a CFG, is our formal rulebook. Now, the phrase context-free is the most important part here. It means a rule applies universally. If you have a rule that says replace variable A with something else, you can do it anytime you see an A, no matter what's sitting next to it. The context just doesn't matter. Let's see this thing in action. We'll use a simple grammar to build the string AAB. We always kick things off with our start symbol, S. First, we apply the rule to wrap S in an A and a B. Then we do it again on that new S in the middle. And finally, we replace that last S with AB. And just like that, by following the rules, we've derived a valid string in our language. But sometimes these grammars can get a little tricky. A grammar is ambiguous if there's more than one way to derive the exact same string. For a calculator, that'd be like not knowing whether to do addition or multiplication first, which is a huge problem. In programming languages, we get around this by designing unambiguous grammars that use rules for things like operator precedence.
All right, we've got the blueprint, the context-free grammar. Now, let's meet the machine that can actually read it, the pushdown automaton. And this just illustrates the core idea so perfectly. A pushdown automata, or PDA, is just a finite automata with that stack memory we talked about. That's it. It's the same machine, just with a new tool that lets it remember things.
So, how does this new machine actually work? Let's trace it recognizing our AABB string. It starts with the full input ready to go and an empty stack, except for a special marker at the bottom. As it reads that first A, its rule is simple. Push is symbol onto the stack to remember it.
It does the same thing for the second A. The stack is now a perfect mirror of the A's it has seen, acting as our memory. So now we have two A's on the stack, and we're ready to start seeing some B's.
Okay, now the game changes. When the machine sees its first B, its rule is to match it by popping an A from the stack. It consumes the B and removes an A from its memory.
It does the exact same thing for the final B and the final A. And look what happens at the end of the process.
The input is empty, and the stack is also empty, right down to our initial marker. That's the signal for success. The machine accepts the string because everything matched up perfectly. The memory was used up exactly as the input was read.
Now, not all PDAs are the same. A deterministic PDA always has exactly one move it can make, but a non-deterministic PDA can explore multiple paths at once. And here's what's cool. Unlike with finite automata, this non-determinism actually makes the PDA more powerful.
It lets it recognize things like palindromes, words that read the same forwards and backward. To do that, the machine has to basically guess where the middle of the word is so it knows when to stop pushing letters onto the stack and start popping them off to check for a match.
The PDA is powerful for sure, but it's not all powerful. Adding one stack gave us a huge boost, but it still has its limits.
So how do we find these limits? Well, there's a fascinating property of all context-free languages called the pumping lemma. The key idea is that because these languages are built from a finite set of rules, any really long string must have a nested, repeating section inside it that you can pump or repeat infinitely, and the new string will still be valid. If a language doesn't have this pumpable quality, it just can't be context-free.
So why does this matter? Think about the language with an equal number of A's, B's, and C's. A PDA can't do it. Intuitively, it can use its stack to count the A's and then match them against the B's. But by the time it gets to the C's, the stack is empty. It has no memory of how many A's there were to begin with. One stack can only handle one dependent count.
This brings us to the big picture. Context-free languages and PDAs aren't the beginning or the end. They are a crucial step on a ladder of computational power, known as the Chomsky hierarchy.
This table, the Chomsky hierarchy, lays out the entire landscape of computational power. We started at the bottom with Type 3, the simple, regular languages. Today, we've climbed one rung up the ladder to Type 2, the context-free languages. As you can see, there are even more powerful machines and more complex languages beyond this, leading all the way up to the Turing machine, the theoretical model for all of modern computing.
And that leaves us with a final thought to chew on. We saw that adding one stack to a finite automaton created the Pushdown automaton and unlocked this entire world of context-free languages. So what happens if we give our machine a second stack? What new powers would that unlock? Well, that's a question for another time. Thanks for joining me.